finishing that. We only have 2 slides left. My timing has not been good. Oh, wow. So this is more on a luminescence, right? And this is an example of a luminescence experiment. So this would be a fluorometric assay of selenium in Brazil nuts. So one of the ways that's most prevalent to measure selenium in Brazil nuts is you would take 0.1 gram of the nut. You would then digest that 0.1 gram of the ground up nut. You guys remember how to do that, right? We've done that a few times with pills, right? Same sort of digestion. 2.5 milliliters of 70% by weight nitric acid. What this is going to do, it's going to digest the matrix down so that you can get a selenium and just a few other things, okay? So the H2SeO4 in the digest is reduced to H2SeO3, which is selenite. This is then, derivatized to form a fluorescent product. You would then extract it into cyclohexane. So right here, this is the derivatized. So this is actually the fluorescence product that you're going to measure, okay? So right here's the species you're going to digest and you'll get out of that Brazil nut. See that? You're going to put it with this form right here at pH 2, which is the acidic conditions, right? That we have. At 50 degrees Celsius, which means that you're heating this very gently, right? And this will give you a fluorescent product. Why is this the fluorescent product? We'll note that we have these conjugated rings, right? You guys remember those conjugated rings had very nice absorption bands that matched up with the UV vis, right? Okay. So this is going to have very nice absorption bands, and thus the mirror image, the fluorescence bands, will be very nice and distinct, right? Okay, everybody good so far? All right, very good. Note that it would be very difficult to measure any of these forms of selenium, okay? They're ionic, they have multiple species in solution, right? It would be much more difficult. So you get it all into a form that's much more easy to measure, okay? The maximum response of the fluorescent product, this is the fluorescent product again, this was observed with an excitation wavelength of 378 nanometers. Excitation wavelength would be the wavelength you'd put in, right? And then it would have an emission wavelength of 518 nanometers. And so that's the one you would then measure for the emission, right? The luminescence. Okay. This right here is the fluorescence intensity, and right here would be the concentration of selenium in that solution. And so you see you get a pretty sensitive measurement right here. Okay? Fantastic. All right. So some analytes, such as riboflavin on polycyclic obviously I haven't had enough water. Excuse me. Aromatic compounds, these are naturally fluorescent. By the way, typically conjugated double bonds are going to be naturally fluorescent. Remember when we did that in organic and how we talked about those always have strong absorptions in the UV vis? Yeah. Riboflavin has it. Many proteins are also naturally fluorescent. Okay? This is one of the reasons you're never going to see Raman work, any Raman spectroscopy done on these compounds. Okay? It's very difficult to do. So you typically don't use Raman spectroscopy because they're fluorescent. Because when you hit them with the beam, instead of getting scattering, you get fluorescence, right? But you get both, which means it's difficult to, the scattering is a much weaker effect than fluorescence. Is that making sense to you guys? Okay. Do you guys understand why scattering would be a weaker effect? Okay. So, like absorption and fluorescence or luminescence, these are both direct consequences of getting hit by that light, right? So when you get hit by the light, you have either or you can have both an absorption and then a fluorescence, right? Okay. Some things just absorb and then don't fluoresce. You have to absorb somehow to get fluorescence, so. Okay? Now, that means that whatever molecules happen to be in the pathway, as long as you have the right frequency of light, you're getting one of those, right? Or maybe both. Now, with scattering, that's a random chance, okay? So what do I mean by Raman scattering? Well, which is called the Smeckel effect, if you're ever curious. That's the person that actually worked it out mathematically. And that would be the actual correct name for the technical effect that causes Raman scattering. Okay, but I'm not gonna test you on that ever. That's a much more advanced topic. So when you get Raman scattering, a Smeckel effect, what you get is you have to have excitation energy already there, or you have to lose some amount of that energy and then going down to an excited state, right? And so the amount of where you have a difference in that frequency and actually have a Raman effect, like 99% of the time, you won't actually get a Raman effect, okay? And so the luminescence and the absorption spectras are far stronger, almost 100 times, if not more, stronger than the Raman effect, okay? And again, remember, the Raman effect is actually what we're looking at for the sky, in case you're wondering. Which is why you can look at the sun and it doesn't look blue, right? If the Raman effect was a large portion, was anything near the absorbance and fluorescence, then the sun would start looking blue, okay? All right, anyways, the fluorescent moiety, this is such as fluorescein, can be decoupled to other molecules in order to form derivatives that fluoresce. What does that mean? Well, you may remember we actually used fluorescein. Do you guys remember that at all? And one of the reasons we did it is because you can hit it with like black lights and see it really nicely, right? In fact, we took advantage of that on the chromatography. You guys remember a coupled fluorescence from fluorescein. Neat, huh? We've actually already seen this in organic chemistry. So this is one of the most common ways, is essentially bind something that already fluoresces to something that you want to fluoresce, okay? It will change the fluorescence behavior of what you bind, and that will give you something that fluoresces at a new wavelength, okay? That makes sense? It's actually a pretty nice and easy way to do it, right? You've already seen this a lot. You ever seen chemiluminescence? Yeah, you know the spray they do for like blood? That's a form of chemiluminescence, okay? And that's luminol right here. And so you put that with some sort of oxidant, like the oxidants that are in the atmosphere, or you can actually add the oxidants yourself, and you put it with a metal catalyst, like, say, iron from the heme group in blood. And what will you get? Well, it will actually start luminescing blue light. That's chemiluminescence right here. And that's why if you spray a crime scene with that, and there's blood samples, turn off the light, you can start getting the chemiluminescence, right? You may or may not have to actually give it a energy to overcome the reaction barrier, the activation energy. If you do, you can do like black lights, that sort of stuff, to give it the energy to go faster. Okay, you'll get it more intense, but it should actually give you a blue light right off the bat, as long as you mix the mixture correctly. Now, a side note to this is you have to mix this up fresh every time. If you use old chemiluminescence, it will slowly react and degrade, okay? So you have to put the oxidizing agent in with the luminol, and you have to keep the luminol away from oxidizing agents in the catalyst, which is not as easy as you might think. And this is why a lot of people try to demonstrate that, and it fails horribly. You guys have no idea how many demonstrations I've seen fail. All right. Do you have any questions on any of that? Okay, we're going to go in chapter 19 now.